you feeling heavy? Do you have a weight on your back that's too hard to carry? The wind is you still in your tracks. Well, tell me, are you hurting? Do you have a burden like a chain on your neck? Well, let me tell you something. You don't have to live like that. No one soul could never make it alone. But if we all stand together, then we're stronger than one. And when your world starts to crumble, you don't have to run. 'Cause if we all stand together, then we're stronger than one. And have you been rejected? I promise I've been there too. I know how it affects you in every single thing that you do. Are you brokenhearted, feeling disregarded, like you got nothing left? Well, let me tell you something. You don't have to live like that. No one soul could never make it alone. But if we all stand together, then we're stronger than one. And when your world starts to crumble, you don't have to run. 'Cause if we
We're just talking into this?
Yes, I think so.
Okay.
Yeah, they said they didn't have a lapel.
Hello, everybody. Please come on in and take a seat. We're ready to start the next tutorial. The next tutorial will be on meta-learning, always a popular topic, from few-shot learning to rapid RL. And who better to give that tutorial than Sergey Levine and Chelsea Finn. Sergey has been at UC Berkeley for the last 5 years? 3 years. 3 years, a very productive 3 years. As a professor, and Chelsea has just finished her PhD at Berkeley, is currently spending some time at Google Brain, and will be starting her own lab at Stanford University as a professor in the fall. Together, they have 6 papers at ICML this year, and enjoy seeing those in the days to come. And without further ado, Chelsea and Sergey.
Thank you for the introduction, Raya. We're excited to be giving this tutorial on meta-learning. Throughout the tutorial, we encourage you to be thinking about questions that you might have about the content that we're presenting. And as you go through, if you have a question, you may come up to one of the 4 microphones. But also, if you want to also ask a question from your own seat without having to get up, we have a link that will allow you to post questions and to also upvote other questions. And we'll be monitoring that and also asking questions throughout from that link. So that's slido.com/meta, but we'll also have the link on future slides. Also, we posted a PDF version of these slides at tinyurl.com/icml-meta-slides. And so if you don't want to be putting your phone up to take pictures of the slides, then you can look at the slides there as well. Great, okay. And additionally, we'll also be taking questions at the break and at the end of the tutorial. So let's get started. So a lot of the motivation for meta-learning comes from being able to learn from small amounts of data. And in particular, what we've seen is that meta-learning thrives with large data sets. If there's one thing to take away from the last few years of machine learning research, I think it's that large, diverse data sets plus large models leads to broad generalization. We've seen this time and time again, from systems trained on ImageNet to transformer models trained on large machine translation systems to GPT-2 trained for large-scale language modeling. And all of this falls under the paradigm of deep supervised learning. But what if you don't have a large data set? What if you're in a domain such as medical imaging or robotics or translation of rare languages or recommendation systems? In each of these situations, we don't have a large data set for every possible task, every possible switch situation, or every possible person we want to personalize our machine learning system to. Or what if you want a more general purpose AI system that can do many different things, that you want to be able to continuously adapt and learn on the job? If so, it's impractical to learn each and everything from scratch for doing the task. And so instead, we want to be able to very quickly learn new things based on our previous experience. And finally, what if your data has a long tail? For example, what if the number of data points starts going down significantly as you encounter more objects or as you interact with new people, hear new words, and encounter new driving situations? In these situations, your standard machine learning systems will do well in the kind of the big data regime, but as you move towards having fewer examples, these systems will start to break down. And in particular, not only in the long tail setting, but in all 3 of these situations, these settings start to break the standard supervised learning paradigm. Okay, so what I'd like to try out next is actually give you guys a test. So supervised learning breaks down here, but actually humans are pretty good at these situations. And I want to give you a few-shot learning test. And your goal is I'll give you 6 training data points, which are shown on the left. The 3 on the first column are from the painter Brock, and the middle 3 are from Cezanne. And your goal is to be able to classify the painter for the painting shown on the right, who painted that painting. And this is a few-shot learning problem because you only get 6 data points in order to do this task. You get 6 labeled data points for this binary classification problem. Okay, so raise your hand if you think that the painting on the right was painted by Cezanne. Okay, and raise your hand if you think that the painting was drawn by Brock. Okay, great. So most of you got the right answer. So this is indeed by Brock. And the way that you can recognize this is that there's kind of some more straight lines and more kind of high contrast lines in the painting. And so how do you accomplish this? So this sort of thing, learning from only 6 examples would actually be extremely hard for a lot of modern machine learning systems. And yet all of you guys were able to do it, or most of you guys were able to do it quite well. So the way that you were able to accomplish this was because you have previous experience. You weren't trying to learn from these 6 examples from scratch. And many of you probably haven't seen these particular paintings before, or maybe you haven't even seen paintings from these particular artists before, but you have experienced different shapes, different textures. You've probably seen other paintings before. And through that previous experience, you're able to figure out how to solve this task from only 6 examples. OK, so now, how might we get a machine learning system to solve this task? Depending on what era you're in, you would probably answer differently. You might try to model the image formation process. You might try to model the geometry of different objects in the image. If you're using slightly more sophisticated techniques, you might use something like HSIF features or HOG features with a support vector machine. Or more recently, maybe you try to fine-tune from ImageNet features or try to do domain adaptation from other painters, for example. And maybe in the future, we'll be doing something even more sophisticated. So these different approaches may seem very distinct in the kind of the approach that they're taking, but they all share one thing in common, which is all of them are different ways to inject previous knowledge or previous experience into the system. And as you move down these prior knowledge, you get few human-engineered priors and more data-driven priors. And also, as you move down, you get systems that work undoubtedly better. And so in this tutorial, we want to try to take this one step further. And in particular, we want to be able to learn priors explicitly from previous experience that lead to efficient downstream learning, an entirely data-driven approach to acquiring these priors. That is, can we have these systems learn how to learn to solve tasks? And this is what is known as meta-learning. In the rest of this tutorial, Sergey will first talk about the problem statement and overview the general meta-learning problem. Then we'll be talking about different meta-learning algorithms ranging from black box adaptation approaches to optimization-based approaches to non-parametric methods. Then we'll discuss how we can develop Bayesian variants of each of these methods. Then we'll talk about how meta-learning has been applied to different application areas. We'll take a short 5-minute break and also allow additional questions. Sergey will then talk about meta-reinforcement learning, and we'll conclude by discussing challenges and frontiers. OK, next, Sergey will be talking about the problem statement and overview.
Thank you, Chelsea. And those of you that were trying to find the slides, there was somebody who actually posted the link. Again, if you go to the thing on the slide here, the Slido/meta, the first question is actually a link to the slide deck. So if you want the slide deck, please check that out there. All right, so let's start with a discussion of how we can actually formulate the meta-learning problem. And there are really kind of 2 distinct viewpoints on meta-learning. There's kind of a mechanistic view and a probabilistic view. Let me explain what I mean by these. The mechanistic view looks at meta-learning as a setting where there's a deep neural network model that can read in an entire data set and then make predictions for new data points. Training this network uses a metadata set, which itself consists of many data sets, each for a different task. And this view of meta-learning makes it easier to implement meta-learning algorithms. So if you're actually coding something up in TensorFlow or PyTorch, the mechanistic view is probably the one that makes it clearest. The probabilistic view treats meta-learning as the problem of extracting prior information from a set of meta-training tasks that allows for efficient learning of new tasks. This view says that learning a new task basically uses this prior plus a small amount of training data to infer the most likely posterior parameters that will allow you to solve this task. And this view of meta-learning makes it easier to understand meta-learning algorithms. These are not 2 views that result in different methods. They're actually 2 viewpoints that can be taken to understand the same methods. So in this part of the tutorial, I'll actually focus on the second view, on the probabilistic view, because our aim is really to help everybody to understand meta-learning algorithms. But we'll see the more mechanistic view emerge when we talk about particular practical instantiations of these methods. OK, so just to work towards a problem definition for meta-learning, let's first start with a problem definition for regular supervised learning and cast it in a probabilistic framework. So a lot of what I'm going to say, some of you might have already seen maybe in a course on machine learning or a textbook, but I just want to walk through it step by step because the meta-learning problem definition will build on this. So if we're doing supervised learning, what we're really doing is we're finding the most likely parameters phi given our data d. So phi denotes the parameters of your model. So if you're training, for example, a deep neural network model, phi literally refers to the weights. D refers to your training data. So it's a set of tuples of input-output pairs, where the input might be something like an image, and the output is maybe the label corresponding to the class of the object in that image. Now, when we actually want to do this kind of maximum likelihood estimation problem, we typically apply Bayes' rule and rewrite it as the sum of log p of d given phi plus log p of phi. And the first term is typically referred to as the likelihood of your data, and the second term is the prior or the regularizer. So if you're using weight decay, that corresponds to a Gaussian prior, for example. And if we factorize the likelihood, if we assume independent and identically distributed data points, then we get the familiar form shown here. It's a sum over all of your data points of the log probability of the label yi given the input xi and your parameters phi. So this is essentially supervised learning. Now, of course, there are some things that are a little bit problematic about this, as Chelsea alluded to in the motivation. The models that will work best, the most powerful models, will typically require large amounts of data. So if your data is very limited, it might be very difficult to get a very accurate posterior, a very accurate estimate of phi. So the problem at its core that we're going to be dealing with in meta-learning is how do you do a good job of estimating phi when your data is limited? And the way you're going to do that is by incorporating more data that is not exactly for the task that you want, but somehow structurally related. So the question is, how can we incorporate additional data? And I should say, as an aside, this is very much the same kind of challenge that things like semi-supervised learning and unsupervised learning deal with. So in semi-supervised learning, you incorporate additional data that doesn't have Ys, and so forth. In meta-learning, you incorporate additional data that we're going to call d-meta-train, which is labeled data. It's just labeled data for different tasks. So d-meta-train is actually a data set of data sets. So it's a set of data sets d1 through dn, where each of those data sets di itself consists of a set of tuples xi and yi, where those y's are labels for different tasks. So we assume the tasks are somehow structurally similar, but not actually the same. So you can't just directly incorporate d-meta-train as training data into supervised learning. Let me give a little example. This is based on a popular benchmark for meta-learning called the mini ImageNet dataset. Let's say that your few-shot classification task requires you to do 5-way classification between cats, dogs, lions, worms, and stacks of bowls. I don't know why you would want to do this task, but let's say this is a few-shot task and you have only a few examples of each image. Now, those few examples are not enough to solve the task by themselves. So we're going to use d-meta-train, which is a collection of data sets for other 5-way classification problems. So maybe one of them classifies, birds, mushrooms, dogs, singers, and pianos, for instance. Different tasks, but some structural similarity because all of them are visual recognition tasks. Another example, maybe the task you want to solve is a few-shot regression problem. You have a few examples of input-output pairs, but then your meta-training tasks consist of other curve-fitting problems, so other curves with a few sample input-output pairs. Or maybe you have some kind of speech recognition task or some kind of language translation task and so on. So in all of these cases, you can formulate a set of meta-training tasks that are not the same as the task you want to solve, but somehow structurally similar. And typically, these would come from your prior data. Now, we could simply stop right there and treat meta-learning as a non-parametric learning problem. So you want to basically use D and d-meta-train together. But oftentimes, if we want to use high-capacity models, we don't want to store all of our data and keep it around forever. We'd like to somehow distill it into a model, into a parametric model with learn model parameters. So in meta-learning, we don't want to keep d-meta-train around forever. What we'd like to do instead is learn some meta-parameters theta. So we're going to use d-meta-train to learn theta, and theta will basically contain all the information that we need for solving new tasks that we've extracted from d-meta-train. So whatever we need to know about d-meta-train is going to be baked into theta via a meta-learning process. And that's essentially the essence of the meta-learning problem. Now, if we want to treat this probabilistically, what we can do now is we can say, well, we can write out our p of phi given d comma d-meta-train as an equation where we're integrating out these sufficient statistics of our meta-training data called theta. And this implies the assumption that phi is conditionally independent of d-meta-train given theta, which is very reasonable because we just said that theta should be whatever extracts all the necessary sufficient statistics from d-meta-train. Now, in reality, integrating out theta is computationally very, very expensive, so we wouldn't want to do this. What we would want to do in practice typically is use a maximum a posteriori estimate, which means that we're going to approximate this integral with just a point estimate for theta star, where theta star is whatever actually maximizes the log probability of theta given d meta train, which again is a very standard thing to do in machine learning. So this argmax that I have written on the right side here, this is the meta learning problem. The meta learning problem is to pull out the right theta from your meta training data so that that theta contains everything you need to know to efficiently solve new tasks. And efficiently solve new tasks means figure out phi. So once you have theta, the problem of getting phi can be written as the argmax of log p phi given d comma theta star, because you don't need the d meta train anymore. That's all been baked into theta star. Okay, so that's the basic problem formulation. If anybody has any questions, feel free to come up to the microphones and ask me. Otherwise, I'm going to move on to a simple example. Chelsea, there's a question online.
Yeah, so there's a question on Slido that says that is meta learning the same as transfer learning? And if not, what is the difference?
Yeah, that's an excellent question. So meta learning is conceptually quite related to a number of other problem settings, including transfer learning, multitask learning, even things like semi-supervised learning, in that all of these problem settings deal with incorporating additional data that is not quite from your task, but is going to help you solve your task more efficiently. The main difference is that meta learning deals with a setting where you still have to do some amount of adaptation on your new task. Transfer learning, formulated in certain ways, can actually be viewed as a type of meta learning as well. I'll describe related problem settings a little bit more at the end of this section, and maybe then things will be a little clearer. Okay, let's continue. So let's work through a little example of how we can design a cartoony version of a meta learning algorithm. Chelsea will talk about much more practical algorithms. This is just meant to be an illustration. So first, let's talk about the adaptation. Let's say that we already have this theta star. We don't care how we learn it, and now we just want to classify new data points using a small data set D. So classifying new data points means your test data point x test goes in, your label y test comes out, and this function that does this is somehow parameterized by theta star. So theta star determines the mapping between x test and y test. Where does theta star come from? Well, it comes from using your data set D, which might be a small data set for your new task, together with your theta star. So D is going to be read in by some function, and that function that reads in D is parameterized by theta star. Sorry about that. So that function is parameterized by theta star. Now, you would also like to, of course, be able to learn this theta star using large amounts of meta training data, which I'll come to in a second. But if you can somehow use that meta training data to get theta star, then that will process your data set, output phi star, and allow you to turn your test inputs into test labels. So theta star is what parameterizes this function. Okay, so now how do we actually train this thing? Well, as I alluded to before, it's going to involve this meta training data. And the key idea behind setting up meta learning algorithms, I think, is best summarized by this sentence from a paper by Vinyals et al. Called Matching Networks, which says that our training procedure is based on a simple machine learning principle, which is that test and train conditions must match. Now, let's unpack this a little bit. What are the test conditions? Well, test here refers to meta test, right? So meta test time is adaptation. The test condition is that a model parameterized by theta star reads in D, outputs phi star, and phi star is then used to classify new data points for your task. So the training time conditions need to match. So at meta training time, you also need to have a model that reads in a data set. Which data set? Well, a data set DI from your meta training set. It is going to be parameterized by theta. It's going to output phi star, and that phi star needs to be good for classifying points. Which points? Well, that's maybe the puzzle. So what is it that we're actually going to classify here? What we need to do in order to complete the meta learning problem definition is we need to reserve a little test set for each task. So it's not enough to just have a training set. The training set is what the model needs to read in, but then it needs to be trained on something. And what it's actually going to be trained on is a little test set for each task. So for every one of our few-shot tasks, we're going to assume that we have k training points, but then also some number L of little test points. And those test points are what's going to supervise the meta learning. They're not used for adaptation. They're just used for meta learning. So D test is where X test and Y test will be sampled from. So the game that you're playing then is read in D train, output phi, and make sure that phi is good for classifying points from D test for that same task. So now we can actually complete the meta learning problem definition. So the adaptation step we can write more compactly as some function f theta star of dtrain. So f theta star reads in dtrain and outputs phi star. So now all we have to do is learn theta such that phi equals f theta dtrain is good for dtest. So for every task I, you want to read in dtrain I and be good for dtest I. Which means that we can write down the meta-learning problem formulation like this. Theta star is the argmax for the sum over all of your tasks of log p phi I given dtest I, where phi I is equal to f theta applied to dtrain. So notice that we get phi from dtrain, but we meta-train on dtest. We can also represent this with a graphical model. So if you're into graphical models, here's a graphical model that represents this relationship. So you have theta, which are your global meta-learn parameters. For every task, you have a phi I, and x train together with phi I determines y train, and x test together with phi I determines y test, and y test is observed during meta-training, but not observed during meta-testing. That's why it's kind of half-shaded there. Okay. So this basically defines the meta-learning problem, but let's kind of round out this explanation with a little bit of an overview of terminology, because we'll see a bunch of this terminology pop up again and again during the tutorial. So we make a distinction between meta-training, meta-testing, training, and testing. So you're learning the parameters theta during a meta-training phase. That meta-training phase trains on a collection of data sets, each of which is separated into a training set and a test set. So when we say training set, we mean that small few-shot set for a particular task. When we say test set, we mean the corresponding test images. When we say meta-training, we mean the whole set of tasks. So meta-training consists of multiple tasks, each one with a training set and a test set. And meta-testing is what happens once you're done meta-training and you want to adapt to a training set for a new task. So the set of data sets is called d-meta-train. That's what we'll refer to it as. These are meta-training tasks. We're going to use TI to refer to meta-training tasks. So these are all of our TIs. This is our meta-test task. Oops, sorry. And then sometimes you'll hear people say support set and query set. So support is basically synonymous with training set, and sometimes people use support set just to avoid the confusion between meta-training and training. So if someone says support, they mean the inner training set. And when someone says query, they're referring to the test, the inner test set, not the meta-test, just the test. So the query is the thing that you actually want to classify correctly after reading in the support. And if someone says like, oh, I have a k-shot classification problem, what they're referring to is the number of examples. If someone says I have a 5-way classification problem, they're referring to the number of classes. So if you say I have a 5-shot, 5-way classification problem, that means I have 5 classes, each of which has 5 examples. There's a little bit of confusion about the word shot. Sometimes it means the number of images per class, and sometimes it means the total number of images. Usually we'll use it to mean the number of images per class. So 5-shot, 5-way means 25 data points. Okay, now just to wrap up, a few closely related problem settings that are good to be aware of. And this is coming back to that question about transfer learning from before. So meta-learning is closely related to a few other things that we can actually cast as within the same terminology. So multitask learning deals with the problem of learning a model with parameters theta star that immediately solve multiple tasks. So you can think of multitask learning as sort of zero-shot meta-learning. So that corresponds to just finding parameters that immediately solve all the tasks at the same time. This is usually not possible in meta-learning problems. You can't have one model that classifies, that does the 5-way classification with dogs and lions and also with, the pianos and the cats. But you can view multitask learning as a special case where phi is just equal to theta. Another very closely related problem setting is hyperparameter optimization and AutoML. These can be cast as meta-learning. They are essentially meta-learning problems. They're outside of the scope of this tutorial, but I'll just mention briefly how they can be related. So in hyperparameter optimization, you can say that theta refers to your hyperparameters. That's what you're going to get out of your meta-training set. And phi is the network weights. So you'll learn your hyperparameters from d-meta-train, and then you'll use them to get phi. Architecture search, same deal. Theta refers to the parameters of your architecture, and phi is the actual weights in the model. This is a very active area of research. Unfortunately, it's outside the scope of this tutorial, but hopefully this will tell you a little bit about how they relate. Okay, and next Chelsea will discuss a number of actual meta-learning algorithms that we can use based on this problem setting. Oh, yes, and we'd be happy to take any questions right now, too.
Yeah, so one quick question from from Slido is, can you elaborate more on the structural similarity that's required between the meta-training tasks?
Yeah, so in regard to the structural similarity between the meta-training tasks, this is, we can actually make that notion formal. The way we make it formal is we say there's a distribution over tasks. There's a distribution P task, and you assume that all of your meta-training tasks are drawn from that distribution, and you assume that all of your meta-test tasks are drawn from the same distribution. So this is the meta-learning analog of the standard supervised learning assumption. Now, what does a distribution over tasks really mean? Well, that's sometimes ends up being a much more subjective notion. If you have a piece of code that generates your task, then you can say, well, it needs to be generated by the same code. But of course, in reality, those tasks are probably produced by nature, and there it becomes a much fuzzier line. So Chelsea will also discuss a little bit about extrapolation and generalization that perhaps pertains to this.
Great. So before we actually want to start going about evaluating meta-learning algorithms, or going about designing meta-learning algorithms, we need to figure out how to actually evaluate a meta-learning algorithm once we have one. And so it's worth mentioning that there, a lot of the modern meta-learning advances and techniques were motivated by some work done by Brendan Lake in 2015. And Brendan introduced the omniglot dataset, which is much more simple than the mini ImageNet dataset that Sergey was showing on the previous slides, but allows us to really study some of the basics of meta-learning. So the omniglot dataset, it has 1,623 characters from 50 different alphabets that are handwritten, things like Hebrew, Bengali, Greek, Futurama, and for each character, there's 20 handwritten instances of that character. And so one of the interesting statistics of this dataset is that it has many classes and few examples per class. And this is actually quite different from a lot of standard machine learning data sets, such as MNIST, for example. It's essentially the transpose of things like MNIST that have few classes, 10 classes, and many examples per class. And what I find really appealing about these kinds of data sets is that they're more reflective of the statistics of the real world. In the real world, we have tremendous diversity in terms of the number of objects and number of items and people that we encounter, and we don't encounter them over and over again. We often encounter many new things constantly throughout our lifetime. Okay, so this data set proposes both few-shot discriminative and few-shot generative problems, such as recognizing new characters, generating new data sets, for example. And initial approaches for this data set and for other data sets for few-shot learning were based off of Bayesian models and non-parametrics. Similar to what Sergey was mentioning before, in addition to the simple omniglot data set, which in many ways actually methods are doing quite well on these days, we have also been using things like mini ImageNet, CFAR, CUB, Celebe, and other data sets for evaluating meta-training algorithms. And many of these were not necessarily initially purposed for meta-learning, but we're able to kind of put them into the purpose that we would like. Okay. So how do we actually evaluate a meta-learning algorithm? This is similar to what Sergey was discussing earlier, where we have some n-way k-shot classification problem, such as one from mini ImageNet, where we want our algorithm to be able to perform learning from very small data sets. So we might want to be able to learn from one example of 5 different classes to classify new examples or new images as being among one of the 5 classes shown on the left. And the way that we can do this is we can take data from other image classes, structure it in the same way as what we're going to be seeing at meta test time. For example, taking images of mushrooms and dogs and singers, structuring it into likewise these 5-way one-shot classification problems, doing this for many different other image classes, training our network in order to perform these types of things across these training classes such that an evaluation is able to solve the problem on the top with held out classes. And this is an example that's specific to image classification, and we're going to be coming back to this example a number of times because it's useful for comparing different approaches. But the same sorts of ideas are also applicable to things like regression, to language generation and prediction, to skill learning. Really, any machine learning problem you can construct in this way, where you're training it on a number of machine learning problems, and you want it to be able to generalize to learning a new problem with a small amount of data. Okay, So now that we know how to evaluate a meta-learning algorithm, let's actually dig into how we actually design these meta-learning algorithms. So the general recipe and the general principle behind these algorithms is that we need to choose some form of inferring the parameters of a model phi given our training data set and our meta parameters theta. And then once we choose the form of this, we can then optimize it, optimize the meta parameters theta with respect to a maximum likelihood objective using our meta training data. Okay, and many of the different algorithms that we're going to be looking at today really only differ in step one, choosing how we want to represent this inference problem, essentially. And so you can ask, well, can we just treat this as an inference problem? And in particular, neural networks are actually quite good at inference, so maybe we can just use a neural network to represent this function itself. And that's exactly what the first approach will be. So this is what we'll refer to as black box adaptation approaches. And the key idea is for a neural network to represent this function that outputs a set of parameters given a data set and a set of metaparameters. And for now, we're going to be using a deterministic or point estimate of this function p, which I'll denote as f theta. And of course, we'll get back to Bayesian methods later, and so we'll see Bayes a bit later. Okay, so how do you actually try to design a neural network to do this? Well, one thing you could do is you could use a recurrent neural network that takes in data points sequentially and produces a set of parameters phi. And so this recurrent neural network in this case will be representing f theta, and then we'll take the outputted parameters, use those parameters for another neural network that's going to make predictions about test data points. And so these are going to be the data points from dtest. Okay, and then once we have this model, we can train it with standard supervised learning. This is just a standard recurrent neural network. So we can train it to maximize the log probability of the labels of the test data points given the test inputs. And we can do this optimization across all of the tasks in our meta-training data set. We can rewrite this loss function of performing of evaluating predictions of a model as simply a loss function operating over the parameters phi and the test data points. So we're going to write this right here, and this will be used mostly for convenience later on. And then with this form, we can write the full optimization problem as an optimization of the over the parameters outputted by the neural network f theta and the test data set. Okay. So now that we have this optimization objective, how do we actually, what is the algorithm that's used to optimize this? So what the algorithm looks like is we first sample a task from our meta-training data set or a mini batch of tasks. Then for that task, we have a data set, di, and we'll sample disjoint data sets, dtrain I and dtest I from that data set. And then once we have, so I guess what this looks like is, say these are the images corresponding to task I. We want to be able to partition this or basically sample this sample dtrain and sample dtest from this data set. And so we'll assign like so. And then once we have dtrain and dtest, we'll compute the parameters using dtrain and then evaluate those predicted parameters using the test data points. And it's quite important that dtrain and dtest are disjoint such that we're not training for memorization of the labels, but instead training for generalization. And then once we update our meta parameters, then we're of course going to repeat this process for new tasks. And if we use a mini batch of tasks, the gradient in step 4 is going to be averaged across that mini batch. Great, okay, so there's the algorithm. Now how to actually represent the form of f theta? So the form that I have written here is a recurrent neural network. You could use something like an LSTM. You could also use something that another memory augmented neural network, like a neural Turing machine, which has been done in past work. You could also use something like self-attention or 1D convolutions, or even really just a feed-forward network that then averages in some embedding space. The key thing is that you want these networks to be able to take in sets of data points, and oftentimes you want it to be able to take in variable numbers of data points. And so that's why we'll be using these types of architectures that have the capability to take in sets and variable numbers of data points. Okay, great. So now that we've gone over kind of this type of approach and how it works and the different architectures, what are some of the challenges that come up? So one thing that you might ask is, well, if our neural network is outputting all of the parameters of another neural network, this doesn't really seem scalable. What if the neural network that's making inferences about test data points has millions of parameters? Then we need a neural network that outputs million dimensional output. And one idea that we can use to remedy this is we don't actually need to output all of the parameters of another neural network. We really just need to output the sufficient statistics of that data set, of the training task, that allow us to make predictions about new data points. And so what we can do is we can take this architecture, and instead of outputting phi, we can output something like h, where h is representing a low-dimensional vector. And then, and this will be essentially representing information about the task, everything that's needed about the task in order to make predictions. And then you can combine this sufficient statistic h with another set of parameters theta g that are also meta-learned along with the parameters of f, such that with both h and theta, we can make predictions about new data points. And then theta g can be something very high dimensional, and with the combination of the two, we'll be able to make predictions for a new task. Okay, so the general form of what this looks like is you can kind of abstract away this notion of h and just write out the ability to make predictions given a training data set and a new test input, outputting the corresponding label. Okay, before I move on to the next type of approach, are there any questions?
So the one question from the audience was, does the network need to be recurrent, or are there other architectures that could work well?
Absolutely. So as I mentioned on the previous slide, this could be something that's recurrent, like LSTMs and neural Turing machines. It could use something like self-attention or recursive models. But you also don't need to have something that actually is like a sequence-to-sequence model. It could also simply be something that is a feed-forward model and then averages. If you assume that your training data set has fixed length, then you could, of course, also concatenate and use a fully connected network, although the approaches on this slide tend to be a bit more scalable.
There's a question up there.
Question there? I think it's on.
Hello. Hi. So this might be related to the few previous slides. So I'm trying to understand the difference between meta-learning and the learning to learn framework by Jonathan Bechter that he proposed around 1990s. So I think if I understand correctly, the basic idea of learning to learn is that you're trying to learn the inductive bias of the learning problem, which in this case is theta star in your notation. Could you elaborate a little bit more on this similarity or the difference? Thanks.
Yeah, so I'm not sure if I'm familiar with the particular work that you mentioned, but in general, many of the ideas that we're presenting are inspired by work that was done initially in the late 80s and early 90s with older types of neural network approaches. Many of those approaches didn't specifically look at the few-shot learning setting, which we're focusing on this tutorial, but looked at, in general, learning from relatively large data sets. And it's worth mentioning that actually this particular approach up here was actually done, was one of the approaches that was used in the 90s and also by Hawkrader et al. In 2001. But some of the approaches that we'll be discussing in later parts of the tutorial are more new.
Another question from the audience was, can we use meta-learning approaches to solve classical supervised learning problems, and are there any benefits to doing so?
So I think that we'll get to this question a bit at the end. There are situations where, I guess, the main type of problem that you want to be able to address with meta-learning techniques is settings where you want to be able to take in information about a task that takes on the form of some data, whether it be fully supervised or weakly supervised. And so if your supervised problem setting doesn't have that sort of structure where you want to learn from data to solve new problems, then I think it would be quite challenging to apply some of these techniques. But in other situations, maybe your supervised learning problem does have that structure, and these approaches would definitely do well. Okay, so let's move on to the optimization-based approaches. So now that we've kind of talked about one way to kind of make this approach more scalable, is there a way to infer all of the parameters of the neural network in a way that's scalable without having to train a neural network to output all of the parameters? And in particular, as Sergey mentioned before, you can view the problem of supervised learning as an inference problem, where our goal is to infer a set of parameters using data. And the way that we solve supervised learning problems is through optimization. And these optimization approaches are quite scalable. So what if we treat the problem of inferring a set of parameters from data and using metaparameters as exactly an optimization problem? And this is what optimization-based approaches do. And so the key idea here is that we're going to acquire our task-specific parameters phi I through an optimization procedure that depends both on the training data and our meta parameters theta. And the optimization will look something like this, where we are optimizing an objective that looks like the likelihood of the data given our task parameters, as well as the likelihood of our task parameters given our meta parameters, where essentially the meta parameters are serving as a prior. Now, you might ask, well, what should the form of the prior be for our meta parameters? Well, there's a lot of different approaches, a lot of different things that we could do here, but one very successful form of prior knowledge that we've seen in deep learning, for example, is using training from an initialization provided by another data set. And in particular, what we've seen is if we train on things like ImageNet and then fine-tune that model on other data sets, we're able to capture a lot of the rich information and supervision that exists in the ImageNet data set and use it for new tasks. So this is a very successful form of prior knowledge, and of course the way that it works is you have a set of pre-trained parameters theta, and you run gradient descent using training data for your new task. Okay, so this works really well in a number of different situations, but what if your training data for your new task has only a few data points, like the 6 data points that I showed in the example at the beginning? Well, in this case, things like fine-tuning are going to break down a bit because they weren't actually trained for the ability to adapt very quickly, and as a result, you'll either overfit to those 6 examples, or you won't be able to adapt quickly enough and move far enough from your initialization. So this is what we want to be able to do at test time. It'd be quite nice if we can just run fine-tuning on our 6 examples and get some answer, some function. So this is what we want to be able to do at test time. The key idea behind this approach is to explicitly optimize for a set of pre-trained parameters such that fine-tuning with a very small data set works very well. And so what this looks like is we're going to take the fine-tuning process written here. This is just one step of gradient descent, but you could also use a few steps or up to like 10 steps of gradient descent, for example. Then we are going to take where we got after fine-tuning. This can be like phi I, for example, evaluate how well that generalizes to new data points for that task. This is measuring how successful fine-tuning was. And then we can optimize this objective with regard to the initial set of parameters. So we're going to optimize for a set of pre-trained parameters such that fine-tuning gives us a generalizable function for that task. And of course, we don't want to just do this over one task, but we'll do this over all of the tasks in our meta-training data set so that we can learn an initialization that's amenable to fine-tuning for many different types of tasks. OK, so the key idea is to learn this parameter vector that transfers effectively via fine-tuning. OK, so what does this look like at a somewhat more intuitive level? Say theta is the parameter vector that we're meta-learning, and phi I star is the optimal parameter vector for task I. Then you can view the meta-learning process as this thick black line, where when we're at this point during meta-training and we take a gradient step with respect to task 3, we're quite far from the optimum for task 3. Whereas at the end of meta-learning, if we take a gradient step with respect to task 3, we're quite close to the optimum, and likewise for a number of other tasks. We refer to this procedure as model-agnostic meta-learning in the sense that it's agnostic to the model that you use and the loss function that you use, as long as both of them are amenable to gradient-based adaptation. OK, so now that we've gone through the objective again, let's go through what actually the algorithm looks like. So we can take the algorithm that we showed before for the standard, for the black box adaptation approach, and instead of, we want to derive the algorithm for an optimization-based approach, and what we can do is we can simply just replace step 3, that's inferring the parameters with a neural network, with a step that's actually optimizing for the parameters, in this case through gradient descent. So we'll sample a task, sample disjoint data sets for that, infer parameters with gradient descent on the training data, and then update our meta parameters using the test data points. Note that this does bring up a second order optimization problem because you have to compute the gradient in step 4, you have to differentiate through a gradient step in step 3. In practice, a number of standard auto-differentiation libraries like TensorFlow and PyTorch can handle this quite gracefully, and really you don't have to worry about it too much at all, and it also isn't particularly computationally expensive, but we will talk a bit more about ways to mitigate this in a few slides. OK, so now how does this approach compare to the black box adaptation approaches that we mentioned before? So let's bring up the general form that we talked about before, where you have some neural network that's taking a training data point, or a training data set and a test data point, and is producing a prediction for the test data point. It turns out that you can view the optimization-based approach in the same general form. So before we were using like a recurrent neural network to represent this function, But now we're using what I'll denote as fmaml to represent this function, and that is the function with parameters phi that takes in x tests and produces a prediction, where phi is defined as the initial metaparameters plus gradient descent on the training data point. And so essentially you can view the MAML algorithm as a computation graph, just with this funny embedded gradient operator within it. And so really you can just view it as a very similar approach for doing it, but one that has a lot more structure, the structure namely of optimization within it. And also with this view, that means that we can very naturally mix and match components of these different approaches. So for example, one of the things that we could do is learn the initialization that MAML is doing, but also learn how to make gradient updates to that initialization. And that's exactly what Ravi and La Rochelle did in 2017, which actually preceded the MAML work. And this computation graph view will come back again as we discuss the third type of approach. Great. So questions?
All right. How is theta G learned? This is coming back to the black box adaptation.
Yeah, so great question. So theta G, this is going back to the black box, and in that case, we had a very sufficient statistics H that are produced by the neural network, and we also had theta G that was used to make predictions about the test data points. And in that case, theta G is optimized with all of the other metaparameters of F. So it's optimized just like all the other metaparameters.
Another question about the black box adaptation. So will HI be trivial? Meaning, like, why wouldn't HI just learn to recognize which task is fed in and just output sort of like a one-hot indicator for one of the n tasks?
That's a good question. I think that in practice it doesn't. Do you have an answer for that?
Yeah, maybe one way to think about this is it's kind of the same problem as memorizing labels for regular supervised learning. So in the same way that supervised learning can overfit, meta-learning can meta-overfit. So if you start seeing that your model just outputs a task indicator, that can happen if you have a very small number of meta-training tasks, and that's just an instance of overfitting. We'll talk about meta-overfitting towards the end of the tutorial.
Okay, great. Oh, one more.
Another one. I don't know if you know this, but what's theta G for memory-augmented neural networks?
Yeah, so that's a great question. So the memory augmented neural networks question by Santoro et al. Basically, that just used a standard RNN to take in data points, including the test data point. And so in that case, theta G was actually the same exact parameters as theta in F. So H, the sufficient statistics, is simply the hidden state of an RNN, and there is weight sharing across theta G and theta in F, where it's represented by the weights that are shared across time in a recurrent neural network.
So this one is a crowd favorite, apparently. How is all of this related to hypernetworks, where we are interested in giving parameters of a model as output?
Great, yeah. So the first black box adaptation approach is also what is done in hypernetworks. I think that, I'm not completely sure about this, but I think that the hypernetworks paper wasn't particularly focused on meta-learning problems, and looking at other problems where you're going to be outputting parameters of neural networks. But the approach, the algorithm used is exactly the same as the black box adaptation approaches that I mentioned before.
This question I can answer myself. Can we adopt MAML in a framework that we don't have a batch of tasks ahead and instead we get them sequentially? To hear the answer to this question, you'll have to wait until the very end of the tutorial on the last slide, and Chelsea will answer it.
Okay, one quick audience question.
Okay. So this is a question about MML. So if I understand correctly, that MML essentially learns a base model, which kind of in the middle of like the optimal parameter for different tasks. But it is working underlying an assumption that those optimal parameters for those different tasks are not too far away. So if that in some kind of, if you are choosing a model space that the optimal parameter are far away, so that maybe the middle point of the base model, although it is not too far away from each of the optimal parameter, it might be not optimal for any of those. I noticed it in the original paper that you are basically using a pretty simple convolutional neural net, which have fewer neurons. I'm just wondering, will the MML works keeps its performance, like if you are using a more complex model where its parameter space is more complex and bigger?
Yeah, so first it's mentioning that this diagram we like to use for illustration purposes in terms of understanding the algorithm, but it can also be a bit misleading, which is that in many cases, particularly with heavily over-parameterized neural networks, there isn't just a single optimum for the correct solution, there's actually an entire space of optimum. And with those types of problems, we see that it is actually a bit easier to find something where you're simply one or a few gradient steps away. And in fact, in a minute, I'll talk about the expressive power of the MAML algorithm and its ability to adapt even when your tasks are extremely different. With regard to architectures, I'll talk a bit about that, but in practice, we do find that it scales well to larger architectures, but it may require a bit more tuning than other meta learning methods.
Okay, thank you.
Okay, so great. Leaving off where we left off, so MAML exhibits this kind of structure, unlike the black box adaptation approaches, which is it has this gradient operator inside of it, and so it's actually performing an optimization problem both within the meta training process as well as at meta test time. And so one thing that might be quite natural to ask is, using that structure, does that mean that we can generalize better to tasks that are slightly out of distribution? And this is, of course, an empirical question that we're going to study more so than a theoretical question. And so what we're going to do is we're going to compare MAML with black box adaptation approaches such as snail and meta networks. And we looked at the omni-glot image classification problem, and we tried to plot the task variability versus performance. And what we found consistently across the board is, as we move away from the meta training tasks with either zero shear or a scale of 1, we see that, of course, performance drops for all approaches, but that MAML is able to perform better because it has the structure of being able to of running gradient descent at test time, and at the very least, you are still running gradient descent, so you won't be doing significantly worse than what you might be doing with a neural network that you really can't really say anything about if it's just outputting parameters, for example. Okay, so you might say, well, we get this nice structure, but does this come at a cost? Like, as the question alluded to before, do you need to assume that the task parameters are very close to each other for different tasks? And so we studied this question by studying the expressive power of a single gradient step, basically the update that's used in the MAML function. And what we can say is that actually, for a sufficiently deep neural network function f, the MAML function on the right can represent anything that the recurrent neural network can represent on the left, which is that it can represent any function of the training data and the test input. And we can show this under a few assumptions that are relatively mild, such as the non-zero learning rate, as well as unique data points in the training data set. And the reason why this is interesting is that it means that MAML has the inductive bias of optimization procedures being embedded within it, but without losing the expressive power of gradient descent, or without losing the expressive power of deep recurrent neural networks. Okay, great. So let's go back to some of the motivation that we talked about a little bit with optimization-based approaches, where we're saying that the meta parameters serve as a prior. And we talked about how one form of prior knowledge is initialization for fine-tuning. Can we make this a bit more formal and actually better characterize what sort of prior that MAML is imposing on the learning process? And to do so, we're going to look at Bayesian meta-learning approaches that use graphical models. So this is kind of a graphical model similar to the one that Sergey showed before, where phi I is the task-specific parameters and theta is the meta-parameters. So if you want to do meta-learning or learn a prior theta in this graphical model, it's going to look like the following optimization, where we're optimizing the log likelihood of the data given the parameters. You can write this out similar to the equations that Sergey showed earlier as an integration over the task-specific parameters phi, which are not observed. And this is simply empirical Bayes. And we can of course, this integral is quite intractable, and so one thing we can do is we can approximate this integral with the maximum a posteriori estimate of the task-specific parameters phi I. And this is a fairly crude approximation, but one thing, interestingly, that we can show is if you compute the map estimate, basically, gradient descent with early stopping corresponds to map inference under a Gaussian prior with mean at theta and a variance that's a function of the number of gradient descent steps and the learning rate. And this is exact in the linear case and approximate in the nonlinear case. And so what we can see is that through this approximate equivalence, as well as the approximation of the integral with the map estimate, is that MAML is approximating inference in this hierarchical Bayesian model. which I think is useful for providing some intuition for the types of priors that we're learning in the meta-learning process. Okay, so MAML is a form of implicit prior. Are there other forms of priors that we can impose on the optimization procedure? One thing we could do is do gradient descent with an explicit Gaussian prior, the log likelihood of a Gaussian shown here, and this is what was done by Raduswaran et al. In the implicit MAML paper. We could also have a prior used in Bayesian linear regression. In this case, we can't impose a prior on all weights of the neural network, as that would be intractable, but we can impose it on the last layer of the neural network and do that on top of meta-learned features. This was done in Alpaca, another type of mammal. And we can also, this is moving more away from Bayesian methods, but we can also do other forms of optimization on the last layer of the neural network, such as doing ridge regression, logistic regression, or support vector machines. And this is this form of prior is essentially that we want features that are useful for linear classification that can be performed with these methods. And to my knowledge, this last approach, meta-opnet, is the current state of the art on few-shot image recognition benchmarks. Okay, so now that we've talked about optimization-based approaches, let's go through a couple challenges with them. So one challenge is how do you choose an architecture that's effective for embedding this inner gradient descent procedure? And one way to do this is to do architecture search. And one of the interesting things that was found in this paper is it found that highly non-standard architectures that were very deep and very narrow were quite effective for use with MAML. And this is a bit different from standard architectures that work well for standard supervised learning problems. And in particular, on the mini ImageNet 5-way 5-shot classification benchmark, MAML with the basic architecture achieves around 63% accuracy, while MAML with architecture search is able to achieve 74% accuracy, a pretty substantial boost by actually tuning the architecture that works well for it. Lastly, one other challenge that you come up with the MAML algorithm is that you run into the second-order optimization procedure, and this can exhibit different instabilities. One idea for trying to mitigate this is really the dumbest idea you could come up with is to assume that the Jacobian of phi with respect to theta is identity and simply copy the gradient with respect to phi to be the gradient with respect to theta. And this actually works somewhat surprisingly well, oddly enough, on relatively simple problems, although anecdotally we found it not to work well as you try to move towards more complex problems like imitation learning and reinforcement learning. Another thing you can do is automatically learn the inner and outer learning rates. You can also optimize only a subset of parameters in the inner loop, such as the last layer or affine transformations at each layer. You can also try to decouple the learning rate and the Bat-Storm statistics at each gradient step to have fewer decoupled parameters that might cause instabilities. And finally, you can also introduce additional context variables into the architecture to allow for multiplicative interactions between parameters and allow for a more expressive gradient. And so kind of my takeaway here is that there are a range of simple tricks that can help the optimization significantly. Great. So before I move on to non-parametric methods, let's take one question from the audience and potentially some Slido questions.
So do you know how MAML compares to other first-order meta-learning algorithms, particularly Reptile by John Schulman et al.?
So your question is, how does it compare to first-order algorithms like Reptile?
I mean, can it get over some of these problems you just presented in this slide?
And you're asking about the MAML algorithm?
No, like if you use Reptile, which is a first-order method for meta-learning instead of MAML, can it get over some of the second-order gradient problems you just presented here? Or?
Yeah, so as I mentioned on the first idea listed here, both first-order MAML and Reptile by using this crude approximation, you can have a faster optimization procedure, and it potentially can be less stable, but the main benefit that you get from it is it's faster and lower in memory. But we have found that there are a number of problems where these types of first-order methods don't work at all, and you need to use the second-order methods in order to optimize them well.
Thank you.
Why is theta minus phi in the Gaussian prior? This was a few slides ago.
Let's see, in this one. I don't see it on the slide.
Well, okay, but maybe
I would guess probably,
yeah,
probably a typo.
The answer to this question, though, is that the interpretation as a Gaussian prior, it basically says that the prior is on phi, and phi is normally distributed with a mean at theta. The variance of that prior depends on the number of gradient steps you take, which is actually a very natural thing. Basically, the more gradient steps you take, the further away you get from theta. That corresponds to a prior with a wider variance. Next question, is there any guarantee or test that phi is not multimodal, as map will assume unimodality?
Yeah, so it's certainly, this distribution certainly could be multimodal, and this approximation is ignoring that. In practice, we have found that MAML can work quite well on multimodal problems where you have quite different functions that are represented in the task variables. Although you do need a deeper neural network for that. And there are also approaches such as multimodal MAML, I believe, that try to tackle this problem head on and enable you to get more efficient use of your neural network parameters and by allowing it to represent multimodal distributions over phi given theta.
Okay, a couple more quick ones. In the case of orthogonal tasks, would MAML just memorize?
So if the tasks are, if a single function can represent both tasks without relying on the data, then it will just memorize the function and ignore the data in many cases.
Can we do gradient descent for multiple steps to get phi in MAML?
Yeah, absolutely. So you can use a variable number of gradient steps. In practice, we found that up to 5 gradient steps works well, but in practice, you can use more than that if you find it helpful for your algorithm. It does not introduce higher order terms than a second order optimization. It still remains a second order optimization if you go through the math. Okay, great. So let's move on to non-parametric approaches. And so far we've talked about parametric methods in that we're going to be learning a model that's parameterized by phi. And what about using methods that don't have parameters phi? And the motivation here is that in low data regimes, non-parametric methods are quite simple and work quite well. And during meta test time, we're in a few-shot learning setting, and so we are in a low data regime. However, during meta training, we still want to be parametric because we have large amounts of data across all of the meta training tasks. So the key idea behind these approaches is, can we use a parametric meta learner in order to produce a non-parametric learner? Okay. And note that some of these methods that I'll be presenting do precede parametric approaches, but we're presenting them in this group setting to aid in understanding. Okay, so the key idea here is here's a few-shot learning problem, and one of the things you might ask is, well, one very simple thing you could do in this approach is just take your test data point and compare it to each of the data points in your training data. Basically do nearest neighbors by comparing to each of the images. So this is quite a simple approach and quite valid for these types of problems. The key question is, in what space do you compare these images and with what distance metric? For example, you could do pixel space or L2 distance, but that probably wouldn't give you an effective metric over the similarity between these images. And so the key idea behind these non-parametric methods is to learn a metric space that leads to effective comparisons, learn a more semantic metric space that leads to effective predictions on the test data points. Essentially learn how to compare these images to make effective predictions. And so the first very simple approach for doing this is to train a Siamese network to predict whether or not 2 images are the same. So we can train a neural network that takes in 2 images and is trained to output whether or not they're the same or not. So 0 corresponds to them not being the same, 1 corresponds to them being the same class. And repeat this through all of the data in your meta training data set. And so once you've trained this neural network to be able to compare pairs of images, at meta test time, you can then take your test data point, compare it to each of the images in your training data set, and then output the corresponding label to the image that is the closest. Okay, so in this case, meta training is going to be a 2-way classification problem, and then meta testing is going to be an n-way classification problem by doing all of these pairwise comparisons. So now, to improve upon this approach, you might ask, well, can we make meta training and meta testing match? Can we train it such that it can actually perform effective n-way classification? And this was kind of the key idea that Sergey alluded to in the problem definition, which is to try to match meta training and meta testing. In this case, putting an n-way classification problem with nearest neighbors into a neural network. And so we're going to be feeding the training data set as shown on the left into the neural network, comparing this to our test input shown on the bottom, and outputting these similarities, and then training it such that the predictions that it gets out, which corresponds to weighted nearest neighbors, are correct with respect to each of the tasks in our meta-training set. Cool, so this is basically embedding nearest neighbors into a neural network. The metric that we're using can correspond to a convolutional encoder or some other architecture. To get the embeddings of the training data points, this method uses a bidirectional LSTM. And then we get a model that can do n-way classification, is actually meta-trained for n-way classification. Now, if you have more than one example per class, what this will do is it will independently compare the test image with each of those examples per class. And one of the things that might be nice to do is actually to better integrate the information across different examples for our class. To aggregate class information into a sort of prototypical embedding of that class, such that when we do comparisons, we're comparing at a class level rather than at the example level. And this is exactly what prototypical networks does. So they embed each of the data points for a given class, such as the class corresponding to green, blue, or orange, average these to compute a prototype shown as CK, and then make predictions based off of embedding the test data point X test and comparing it to each of the prototypes. And what this looks like is we simply measure the distance X between each of the prototypes. This is denoted as D, and then perform a softmax operation to decide which class it corresponds to. And in this case, D can correspond to Euclidean distance or cosine distance. Great. So this is a simple approach that works quite well. And there are a couple other extensions that we can make upon it. So far we've looked at Siamese networks, matching networks, and prototypical networks that all correspond to some sort of embedding in the nearest neighbors, either to examples or to prototypes. One challenge that comes up is, what if you need to reason about more complex relationships between data points, and we don't simply want to average to create a single prototypical example per class? To handle this, we could learn a nonlinear relation module on the embeddings. So we could essentially learn that D function by embedding each of the pairwise examples and producing predictions for each of them. We could also learn more than one prototype for each class, learning an infinite mixture of prototypes, or perform message passing on the different classes and the different examples in our data set. Okay. So stepping up a bit, let's actually try to think about how these different approaches compare. So you can go back to the computation graph perspective and bring up the kind of computation graph view of the black box approaches as well as the optimization-based approaches. And the non-parametric approach can be viewed in the same exact way. Except here, we're going to be having a new function, which I'll denote as PN for prototypical networks, where the function corresponds to the softmax of the negative distance between the embedded query test data point and the prototypes, where the prototypes are defined as the average embedding of each of the class for that example. And so with this view, again, we can mix and match components of this computation graph to create hybrid approaches among these different three. And this includes things like CAML, which can both conditions on the data with a black box approach and runs gradient descent on the parameters. It's also another hybrid approach is to run gradient descent on an embedding that produces a set of parameters. So this sort of combines all three approaches. And then finally, we can do something like MAML, but initialize the last layer to be a linear classifier equivalent to the prototypical networks classifier. OK. Before we move on to the takeaways, are there any questions about non-parametric approaches or any questions from Slido? No?
There are roughly 200 questions, and I can't sort through them all. But there are a couple of questions that are kind of crowd favorites that are maybe good to take, not to do with non-parametric methods necessarily, but one common theme is, well, can we do meta-training where we have different numbers of classes for different tasks or different numbers of data points for different classes?
Yeah, absolutely. So, and actually, this is a good question to talk about now, too, because these different approaches can handle variable numbers of training data points and number of data points per class and variable numbers of classes. This is something that optimization-based approaches can handle very gracefully because you can simply compute your loss function over different batches of data points very, very naturally. Black box approaches, you can do it, but you need to train it to be able to do that. You need to be able to train it with variable data set sizes and variable numbers of examples per class. And non-parametric approaches can also handle it fairly gracefully, but in practice, we found them not to always work well to variable numbers of data points per class.
So another question, which is kind of a summary of multiple questions, but I think it applies to all three of the methods, is, well, to what degree do meta-learning methods actually learn to use the entirety of kind of a test batch, meaning that they classify multiple images at once, versus are they classifying individual images one at a time? So all the questions about inductive versus transductive are also getting at this point.
Yeah, so I think that it depends on your application. So if you think that you are going to have just a single example that you need to classify at test time, then all of these approaches can handle that setting. And then if you're in the transductive setting and you think that you're going to actually have a test data set that you need to label that corresponds to multiple classes, then you could either independently classify them, of course, or try to actually combine information between them. Different approaches can handle this in different ways. For example, you can use the batch norm statistics to basically transmit information across different tasks or across different examples in your meta test set. And with this, you can actually transmit a fair amount of information through those batch statistics. And there are also more recent approaches that try to learn loss functions that can effectively transmit information across unlabeled examples.
Another common theme in regard to MAML in a few questions here is, well, what are the relative benefits of simply doing pre-training followed by fine-tuning versus doing MAML? And also, can MAML itself be used as just a pre-training stage without any fine-tuning?
So in practice, MAML is certainly training for like fine-tunability to a new task. And so in practice, you really do need to actually fine-tune it to a test task. Although perhaps if you only care about getting good features, then maybe the features learned by the method are something that is reasonable. OK. So some intermediate takeaways of these different approaches. One of the benefits of things like black box approaches is that they are easy to combine with a variety of learning problems, such as supervised learning and, as you'll see after the break, in reinforcement learning. They do involve a challenging optimization problem, and this is a bit of a subtle point, which is that at initialization, because you're not embedding a known learning procedure into the meta-learning process, there's no inductive bias that points you in the right direction for how to learn from the data. And as a result, you have to learn how to learn from the data completely from scratch. And as a result, these methods can often be data inefficient because that optimization process requires time to actually learn how to learn from data. And lastly, these methods do have an intertwined model and architecture. Essentially, the model that you're using to make predictions about data points is inherently intertwined with the model that you're using to take in the training data points as input. OK, as I mentioned before, optimization-based approaches can very nicely handle varying K and large K. The structure also lends well to out-of-distribution tasks. And one of the downsides is that it does involve the second-order optimization, although there are a couple of approaches towards trying to mitigate this. Non-parametric approaches are quite simple, and they're entirely feed-forward. And because they're entirely feed-forward, they're computationally fast and easy to optimize, because you don't need to worry about backpropagating through gradient steps or through recurrent neural networks, for example. They're harder to generalize to varying K. This is more of an empirical observation than a theoretical one. And of course, because they're using non-parametric approaches, they're harder to scale to very large K because the computation grows with more and more data points. OK, and then lastly, these approaches so far have been limited to classification approaches because you're inherently making decisions based on the data points that you've seen so far. OK, and lastly, it's worth pointing out that well-tuned versions of each of these approaches tend to perform comparably on existing few-shot learning benchmarks. So at the performance level, they all perform quite well. OK, so now let's talk about Bayesian meta-learning approaches. So we had this really nice motivation for Bayesian methods, and then we kind of threw that all away in the last 30 minutes or so. And so in particular, what we did is we assumed that this P of phi, given the data set and the metaparameters, is going to be a point estimate, or a deterministic function of the training data point and the metaparameters. And you might ask, well, maybe this is all fine, like we don't really need Bayesian things, but there are many situations where it actually is useful to be representing actually a distribution over the potential functions that we might be encountering. And in particular, because few-shot learning problems only have a small number of data points, they may be ambiguous even when you do have a prior. For example, if your goal is to classify between all the images on the left and all the images on the right, all the folks on the left are smiling, wearing hats, and young. All the folks on the right are not. And so if you get an image that has someone that's smiling and wearing a hat and not young, or not smiling and wearing a hat and young, then it's inherently ambiguous on what the correct label is for these classes, because you don't know if you're supposed to be classifying on the attribute of smiling, on the attribute of wearing a hat, or on the attribute of being young. And so what you might ask is, can we generate hypotheses about the underlying function, like the 3 hypotheses that I mentioned before? Essentially, can you sample from this function p of phi? And this is going to be important for ambiguous problems, but also for safety-critical few-shot learning, such as medical imaging, for learning to actively learn, because if you care about actually reducing your uncertainty about a given function and getting labels for new data points, then you want to be able to reason about your uncertainty over your function space right now. And it's also, and there have been approaches for using active learning with meta-learning. And it's also useful for learning to explore in meta-reinforcement learning, because again, we can try to explicitly reduce our uncertainty by collecting more data. Okay, so how do we go about trying to meta-learn in a way that allows us to generate hypotheses and reason about distributions? So we can bring up the graphical model that Sergey mentioned before, where we're going to have a distribution over our prior parameters theta. We will have a distribution over our task-specific parameters phi I given theta. And then we'll also have probability distributions corresponding to the probability of our training data set given our task parameters and our test data set given our task parameters. And then our goal will be, can we sample task-specific parameters phi I given our training data points and x-test, essentially given all of the observed variables. And because of conditional independence at test time, we don't really need to worry too much about x-test. We just want to be able to sample phi I given x-training and y-train. So black box adaptation approaches are quite easy to extend to this Bayesian setting. So what we can do is we can use amortized variational inference. We can train a neural network to represent a distribution over sufficient statistics. We could also represent a distribution over full parameter vectors phi I, although that might get a bit unwieldy at some point. And so we could train a neural network to represent a Gaussian distribution over H, and then feed this H into another neural network and use ideas from amortized variational inference, such as the reparameterization trick, to train this model in order to effectively produce this distribution. And indeed, various approaches have used this type of approach. For example, Gordon et al. Used this approach where H corresponded to the weights of the last layer of a neural network. OK, so now that we've gone over how you can very naturally apply this with black box approaches, what about optimization-based meta-learning approaches? Can we further extend these to the Bayesian setting? There's a few different ways we could go about doing this, although this is trickier than the simple black box approach. One thing we could do is model the distribution of phi given theta as Gaussian and use the same sort of variational inference for training as I mentioned before, but have our inference network Q perform an optimization over phi. And this is what was done in Ravi and Beatson in 2019. Another thing that we want to do is if we don't want to model P of phi given theta as Gaussian, we can use Stein variational gradient on the last layer of the neural network and do gradient-based inference on the last layer and only have a single set of parameters similar to theta g for all the other layers. And also we could use something like an ensemble of mammals, an ensemble of meta-trained neural networks that allows us to represent basically particles of the distribution. And both of these were proposed by Kim et al. In 2018. Now, one thing you might ask is, well, can we get some of the benefits of both of these? Can we model both a non-Gaussian posterior and do so over all of the parameters? And there is a way that we can do this, in fact. And so let's go back to our graphical model. Say that we want to sample from this. This distribution you can write out as the integral where we're integrating out p theta. Of course, this integral is completely intractable if theta are the parameters of a neural network. But one thing you might ask is, well, what if we knew p of phi given theta and the training data set? if we knew this distribution, our graphical model would be transformed in this way, switching the arrows from the training data set to phi. And then we could simply sample with ancestral sampling. We could sample a theta from the prior, sample phi from this distribution, and get a sampled phi. And so the key idea is what we can do here is we can approximate this distribution phi given theta and detrain as a point estimate using map. Of course, this is an extremely crude approximation, similar to the one that we use in mammal, but it's also extremely convenient. And in particular, if we do this approximation, we can still get samples from P of phi given the training data. And in fact, to do this approximation, we can use the same gradient-based map approximation as shown before, but we don't require doing the intractable integral at the top. Okay, so at test time, what this corresponds to is we'll have an initial set of parameters theta. We'll add noise to sample. We'll add noise to that parameter vector to basically sample a new theta, and then we'll run gradient descent from there. So it's essentially a way to make mammal give you estimates and sample from P of phi given your training data, but doing so in a way that actually will lead to the correct posterior distribution. I didn't go through actually how we train this. That's a bit harder. And for details, you can look at the probabilistic mammal paper on the bottom. We refer to this algorithm as platypus, or a probabilistic latent model for incorporating priors and uncertainty in few-shot learning, which is a bit of a tortured acronym, but we can then get another type of mammal. And what this gives us is it gives us the ability to sample different functions with only a few data points, such as linear functions, sinusoid functions that are inherently ambiguous because there's some noise in the data, as well as represent different classification problems for different classifiers with different decision boundaries, as again shown in the colored dashed lines. And perhaps most importantly, this also is better able to model ambiguous few-shot learning problems like I showed on the first slide. Okay, for further reading on Bayesian meta-learning approaches, you can look at the papers shown here. And next we can go to a couple questions before moving on to applications.
So one question is, if we want to do a Bayesian meta-learning approach, can we just use dropout at test time?
Right, so if you just do dropout at test time, you will certainly get a distribution. There's no guarantee, like if you don't train for that distribution to actually represent the posterior, then you won't actually get the correct posterior over functions.
For probabilistic mammal, you assume that there's no relationship between the training X and the training Y? Question mark.
The graphical model assumes that the labels Y are dependent on the inputs. The labels Y train are dependent on the inputs X train and the parameters phi. Okay. So let's go through a couple applications. This will be quite quick. Meta-learning has been used in a variety of computer vision applications, such as image recognition, modeling the motion and the pose of humans, used for domain adaptation, for example, when you want to adapt to new domains and you have a variety of domains to train on, as well as for few-shot segmentation problems where you want to segment images given only a few labeled pixels. Beyond some of the kind of typical supervised computer vision problems, people have also looked at generative modeling with meta-learning methods. This includes few-shot image generation, few-shot image-to-image translation, where you want to translate between different types of images, where you want to translate things to a new type of animal that you haven't seen before. Also, generation of novel viewpoints given a single viewpoint, as well as generating videos of people from just a single image of that person. Okay, and then another application that people have looked at is imitation learning, where the goal is, given one demonstration of a task, can you learn a policy for that task? And this is quite a fairly simple extension of the supervised meta-learning approaches that we showed before, because you can treat imitation learning as a supervised learning problem. This has been looked at for stacking blocks on top of each other for like temporally extended tasks, also for other kind of robotics control tasks in the real world, as well as for high-fidelity imitation, where you want to very closely match the training demonstration. And also, it has also been used with optimization-based adaptation techniques, such as shown here. So here the goal is to, after seeing a single demonstration of placing an apple into a bowl through teleoperation, the robot is able to figure out how to place the apple into the bowl in new situations. And in this case, the robot had never seen any of these objects before, and so it's adapting to being able to manipulate objects in new objects in this setting. Okay, and also for more advanced topics, you can look at approaches for one-shot inverse reinforcement learning and one-shot hierarchical imitation learning. Now, one thing you might say is, can we take this one step further? Can we do imitation from a video of a human, per se, where our goal is, given a video of a human performing a task, such as placing into the red bowl, can the robot figure out a policy for for performing the task shown in the video, such as placing the peach into the red bowl? And in this case, you need to learn how to learn from weak supervision. And what I mean by weak supervision is that the video of the human has all the information about the task, but is not accessible in a way of kind of a standard machine learning data set. And so we need to do something a bit different here. And in particular, what we're going to do is we can take the mammal objective, or really any meta-learning objective, and the meta objective, the outer objective, is going to be fully supervised, and the inner objective is going to be weakly supervised. So we'll be learning how to learn from weakly supervised data using fully supervised data. And then at test time, you'll run gradient descent using the weakly supervised data. Now, one question you might ask is, well, what if the weakly supervised loss function isn't available, like from a video of a human? In that case, you could actually learn a loss function for performing adaptation, such as a neural network loss function that outputs a scalar value, and you train this loss function such that the gradients it provides are effective for adaptation. Okay, and then lastly, it's worth mentioning that meta-learning for language has been explored in a variety of contexts. This includes adapting models to modeling new programs, such as program induction and program synthesis. This also includes adapting to new languages, such as translating between two language pairs that you only have a small amount of data for by meta-training on language pairs that you have a lot of data for. This also includes learning new words. So this is actually done in the original Matching Networks paper that learns how to use a new word in a new context from a single example usage of that word. And lastly, adapting to new personas, so training dialogue agents to be able to generate dialogue from a particular persona from only a few examples of that persona. Okay, great. So next we will take a short 5-minute break. We will be taking questions during the break, and then after that, Sergey will talk about meta-reinforcement learning. So feel free to stand up and rest your legs, and we'll be answering some questions.